When a fire alarm sounds in a modern high-rise building, the absolute primary structural objective is always immediate mass evacuation. Under stress, human instinct drives us toward the most familiar high-capacity vertical transport available, the building's escalators. Yet modern fire life safety codes dictate the exact opposite response. The moment an alarm actuates, the building's automated systems immediately shut these escalators down. From a raw capacity standpoint, disabling your highest volume transport machinery feels like intentionally throttling movement. But egress capacity is irrelevant if the environment itself becomes lethal. Without structural isolation, an active escalator introduces mechanical hazards that turn continuous transport into a liability. International prescriptive building codes strip escalators of any classification as a primary means of escape. Standards such as MS 1183 downgrade them entirely, treating them strictly as accommodation stairs. This section of the MS 1183 code establishes the baseline, mandating that escalators must be programmed to stop immediately upon actuation of a fire alarm. The engineering logic is stated directly. Continuous movement poses the risk of discharging occupants into a hazard zone. This is a globally recognized parameter. The BS-EN 81-73 standard enforces identical shutdown rules for escalator fire behavior across international jurisdictions. This immediate isolation is known as the Fire Mode Protocol, an automated intervention designed to neutralize the mechanical threats an active escalator creates during a blaze. These standards prioritize absolute structural predictability and strict flow control over theoretical mechanical speed. To understand why the shutdown is mandatory, we have to look at the fluid dynamics of a structural void during an active fire. Large buildings rely on horizontal fire compartments to contain heat and smoke. An open escalator shaft cleanly punctures these defensive boundaries, linking multiple floors. An active escalator compounds this structural vulnerability through the continuous, looping motion of its step band. The physical movement of the stairs creates mechanical forcing. The escalator acts as an impeller, actively pulling smoke from lower elevations and drafting it upward into the unshielded shaft. This forced convection contaminates higher, uninvolved floors exponentially faster than smoke rising passively through a static stairwell. This infographic details the mechanics of accelerated smoke spread, showing exactly how the moving steps draw toxic gases upward into the open architectural space. Cutting the power neutralizes this threat, stopping the escalator from functioning as a smoke distribution engine. The secondary hazard transitions from fluid dynamics to human behavioral psychology under extreme stress. In panic conditions, crowds exhibit a well-documented flaw. They attempt to evacuate via their known point of entry, regardless of safety. Structurally enclosed, fire-rated concrete stairwells are often located behind doors or down secondary corridors, making them easy to bypass. By contrast, central escalators are highly visible. Their motion and mechanical noise act as a powerful false signal, drawing occupants away from safe egress routes. This misdirection actively funnels thousands of evacuees directly into the unshielded smoke draft zones. This panel of the safety protocol shows the danger of evacuation misdirection, contrasting the hazard of the unshielded moving transport with the protected environment of a fire-safe staircase. Rendering the machinery static acts as a cognitive circuit breaker. It forces panicked crowds to abandon the familiar route and seek out structurally protected exits. The final hazard is purely kinetic, driven by the mass and velocity of a panicked crowd. Egress flow rate is a strict mathematical relationship between how fast an escalator feeds people forward and how quickly those people can clear the discharge landing. If the downstream exit path bottlenecks due to smoke, debris, or slower-moving individuals, the clearance capacity drops immediately. An active escalator operates blind. It continually forces human mass onto the obstructed landing at a constant rate, completely ignorant of the blockage. The kinetic pressure builds instantly, resulting in rapid crowd compression, crush asphyxia, and severe entrapment injuries along the moving cone plates. This section illustrates the increased injury potential, highlighting the severe risk of mass pileups when panicked crowds are forced onto a congested landing. Shutting down the system eliminates the mechanical feed pressure. It instantly converts a relentless, continuous feed hazard into a passive set of stairs where occupants control their own pace. For standard commercial and residential architecture, the code-mandated shutdown rule is absolute. However, prescriptive codes fail when applied to massive subterranean infrastructure and ultra-high-capacity transport hubs, where the occupant load is so dense that passive stairwells simply cannot clear the platforms fast enough to prevent mass casualties. This necessitates the engineering exception, abandoning rigid prescriptive codes in favor of highly bespoke performance-based fire engineering. This graphic details the required performance-based assessments, governed by strict standard frameworks like BS 7974, which allow engineers to test alternative solutions. Maintaining an active escalator during a fire is never a default setting. It is a strictly controlled exemption requiring exhaustive mathematical proof. That proof relies on the relationship between two specific variables calculated within the BS 7974 framework. The first is ASET, or Available Safe Egress Time. This is the precise window before heat, smoke, or toxicity makes the zone lethal. The second is RSET, or Required Safe Egress Time. This calculates how long it takes the specific crowd to physically evacuate. The requirement is uncompromising. ASET must mathematically exceed RSET. The mechanical transport must clear the platform entirely before its own induced drafts pull the smoke layer down to head height. This location-specific modeling requires complex fluid and crowd simulations, a stark contrast to the universal shutdown mandated by standard codes. In fire life safety, uncontrolled mechanical transport is inherently dangerous. Harnessing that capacity requires either immediate isolation for shutdown or flawless, mathematically proven execution.